Now friends, the next numerical is the ionization of hydrogen atom is 13.6 electron volt. The energy corresponding to a transition of an electron between third and fourth orbit is. That means we have to find out the energy of the electron when it makes the transition from third to the fourth orbit. How much energy is required? We know the energy of an electron in nth orbit is equal to minus 13.6 upon n square. Right? The energy of an electron in nth orbit En is equal to minus 13.6 upon n square. When the electron makes the transition from third to the fourth orbit, therefore the energy difference E4 minus E3 is equal to minus 13.6 upon 4 square minus 13.6 upon 3 square. Clear? Therefore, E4 minus E3 is equal to minus 13.6, 1 by 16 plus 1 by 9. Sorry, minus 1 by 9. Because the minus sign is taken out of this bracket, so it's equal to minus 0.85 plus 1.51. Therefore, 0.66 electron volt, that much volt is required. That is the energy difference, or the energy is required to make the transition of an electron from third to the fourth orbit in hydrogen atom. Again, the ionization energy of hydrogen atom is 13.6 electron volt. The energy corresponding to a transition between third and fourth orbit is. So here the electron make the transition from third to the fourth orbit. That means the higher energy orbit to the lower energy orbit to the higher energy orbit. How much energy required to this electron? So the energy required to this electron to make the transition from third to the fourth orbit is equal to the energy difference between these two orbits. For that purpose, we know the equation of the energy or the ionization energy of an electron in nth orbit. En is equal to minus 13.6 upon n square. So energy difference between the fourth and third orbit is E4 minus E3 is equal to minus 13.6 upon 4 square minus into bracket minus 13.6 upon 3 square. That minus 13.6 is common, therefore 1 by 4 square, 1 by 16, minus 1 by 3 square, that means the 1 by 9. So simplification of this, minus 0.85 plus 1.51, therefore 0.66 electron volt energy is required to make the transition from third orbit to the fourth orbit. Clear this? Okay. Now next, if the radius of the second orbit is r, then the radius of the third orbit is what? Radius of the second orbit is r. Now, what is the radius of the third orbit? For that purpose, we know the equation of the radius r is equal to n square s square epsilon 0 upon m pi z square. M pi z square. So from this equation, we know that r proportional to the n square. For H atom, hydrogen atom, Z is equal to 1. Therefore, R2, R1 proportional to the N1 square and R2 proportional to the N2 square. Therefore, the radius of, or the ratio of the radius R2 upon R1 is equal to N2 square upon N1 square. Now here the second orbit radius is r given. In third orbit we have to find out. Therefore 3 square plus 3 square upon 2 square. Therefore 9 by 4 R. Therefore R2 is equal to 9 by 4 R. That means the 2.25 R. So this MCQ question frequently asked in board exam. Again, if the radius of the second orbit is R, then what is the radius of third orbit of hydrogen atom? We know the equation of the radius of nth orbit R is equal to n square epsilon 0 upon m pi z square. Z for hydrogen atom both h is constant, epsilon 0 constant, m pi is square constant. Therefore, we can directly write out like this: R proportional to the n square. Therefore, I1 proportional to the n1 square and R2 proportional to the n2 square. Take the ratio: R2 upon R1 is equal to n2 square upon n1 square. Now, n2 is equal to our third orbit and n1 is equal to second orbit. Therefore, 3 square upon 2 square. Therefore, 9 by 4. R2 upon R1 is equal to 9 by 4. Therefore, R2 is equal to 9 by 4 R1, but that is given R. Therefore, 9 by 4 R. Simplification of the 9 by 4 is 2.25. Therefore, 2.25 R is the radius of our third orbit. Clear? Okay. After that, the ratio of the energy of electron in first excited state to the second excited state in hydrogen atom. Now we know the equation of the energy. Energy E is equal to m is to 4 into z square upon 8 epsilon 0 square n square s square. For H atom, Z is equal to 1. Therefore, energy is inversely proportional to the orbit number. Orbit number. Now, for first excited state, N1 is equal to 2. First excited state, N1 is equal to 2 and E1 is our E. We have to find out the ratio E1. And second excited state, N2 is equal to 3. And energy is E2. Energy is E2. Therefore, we can write E1 upon E2 is equal to N2 square upon N1 square. N2 square upon N1 square. N2 is our 3, N1 is 2, therefore 9 by 4. Therefore, the ratio of the energy in first excited state to the second excited state is 9 by 4. That is as similar as this. Here the equation of the radius we use R proportional to the n square. Here we are using the equation of energy. Equation of energy is equal to m e is to 4 z square upon 8 epsilon 0 square n square h square. For hydrogen atom, z is equal to 1. Therefore, E proportional to the 1 upon n square. Remaining terms are constant. M, E, 8, epsilon 0, h, all are the constant. Therefore, energy is directly proportional to the n square. Okay, now, for first excited state, the number of orbit is 2. And for second excited state, the number of orbit is 3. So we substitute the value, we obtain the ratio of the energy E1 upon E2 is equal to 9 by 4. Now next, what is the angular momentum of an electron in n is equal to 5th orbit of lithium atom? Right. Now from Bohr's hypothesis, we have to find out the angular momentum. Angular momentum small l is equal to mvr is equal to nh upon 2 pi. Here the number of orbit n is equal to 5 given. From Bohr's hypothesis, we know that angular momentum L is equal to NH upon 2 pi. N is the number of orbit pi. pH Planck's constant 6.62 into 10 raised to minus 34 upon 2 pi, 2 into 3.14. So as we simplify it, we obtain the answer 5.27 into 10 raised to minus 34 joule into second. So that is the angular momentum of an electron in lithium atom in nth orbit. Here it is not depends on the angular momentum is not depends on the atom. That is only depends on the numbers of orbit. H and 2 pi is constant. Right? The same value of angular momentum for hydrogen atom and other atom. Now next, wavelength of the phase limit n is equal to infinite of Lyman says is. What is the wavelength of the phase limit n is equal to infinite of Lyman says is? Now the equation of wavelength of Lyman says is 1 upon lambda is equal to r 1 upon 1 square minus 1 upon n square. Value of n is greater than 1 for the 2, 3, 4 and so on. Here n is given the infinite, n is equal to infinite. Therefore 1 upon lambda is equal to r 1 upon 1 square minus 1 upon infinite. 1 upon infinite approximates 0. Therefore 1 upon lambda is equal to r. Therefore lambda is equal to 1 upon r. That is the wavelength of the radiation when the electron makes the transition from infinite number of orbit to the first orbit or the ground state. So whatever the radiation is emitted by the electron having the radius is equal to 1 upon Rydberg constant. 1 upon Rydberg constant. So here only we have to use the equation, general equation of the wavelength of Lyman says. This equation is 1 upon lambda is equal to r 1 upon 1 square minus 1 upon n square. Here the Lyman says is given, therefore here 1 square. Right? Now n is equal to infinite, so electron make the transition from infinite number of orbit to the ground state. So 1 upon lambda is equal to r into bracket 1 upon 1 square minus 1 upon infinite. Therefore 1 upon lambda is equal to r. Therefore lambda is equal to 1 upon r. Right? Now the next is also important question frequently asked in board exam. The energy of the hydrogen atom in ground state is expressed in terms of the Rydberg constant r and velocity c, and also h is the Planck's constant. We have to write down the equation of the energy in terms of r, c and h. Now we know that the energy is equal to equation of energy m is to 4 z square upon 8 epsilon 0 square n square h square. But Rydberg constant r is equal to m is to 4 upon 8 epsilon 0 square h cube c. H cube into c. So here we have this m is to 4 and z is equal to 1 for hydrogen atom. m is to 4 upon 8 epsilon 0 square h square already we have. But here in denominator term the c and h is also required. Therefore we multiply and divide it by the c h. By the c h. And for ground state also n is equal to 1. n is equal to 1. Therefore this term is cancelled. To convert into the form of our Rydberg constant, we multiply and divide it by ch. Therefore minus me⁴ upon 8 epsilon 0 square Ch cube into Ch. So is equal to Rydberg constant. Therefore, is equal to minus RCH. That is the equation of energy. Again, the energy of an electron in the nth orbit is minus me⁴ z square upon 8 epsilon 0 square n square square. For hydrogen atom, z is equal to 1, and for the ground state, we consider the n is equal to 1. And also we know the equation of the Rydberg constant R is equal to me⁴ upon 8 epsilon 0 square Ch cube. Right? We end this equation in that form. me⁴ z is equal to 1 upon 8 epsilon 0 square square. Here in denominator we require the Ch cube. So here already we have the h square. Therefore denominator term must be multiplied by Ch. Therefore numerator and denominator both multiply by Ch. So this term is now R, therefore minus RCH. Clear it? Okay. Only we have to arrange according to the equation of the Rydberg constant. Now next. In hydrogen atom, an electron makes the transition from n is equal to 3 to n is equal to 2. That means the electron makes the transition from higher energy state to the lower energy state in time interval of 1.2 into 10⁻² minus 8 seconds. Time interval is given. Calculate the average torque in Newton into meter acting on an electron. Acting on an electron. So here the N2 is about 3. N1 is equal to 2. Time interval is given delta t is 1.2 into 10⁻² minus 8. We have to find out the value of average torque. We have to find out the tau. In rotational motion, we learned about that tau is equal to change in angular momentum with respect to the time. Delta L upon delta t is equal to final momentum, angular momentum upon initial, final minus initial upon time interval. From Bohr's hypothesis, we know that the angular momentum N2h upon 2 pi minus N1h upon 2 pi upon delta t. Now listen here, N2 minus N1 h upon 2 pi delta. 2 pi delta. There is the average torque acting on an electron when the electron makes the transition from N2 to the N1 orbit. Here the N2 is equal to 3, N1 is equal to 2. Therefore, we substitute the value 3 minus 2. H is the Planck's constant, 6.625 into 10⁻² minus 34 upon 2 pi delta t, 2 pi 3.14 delta t 1.2 into 10⁻² minus 8. As is simplified, we obtain the average torque 8.79 into 10⁻² minus 12 Newton into meter. So very easy numerical, but once we read the question, at that time we confuse how we find out the average torque. But already we know the equation of the angular momentum from Bohr's hypothesis. Angular momentum is equal to nh upon 2 pi. And we know the equation of the torque. Torque is equal to change in angular momentum with respect to the time. There is the Newton's second law for rotational motion, similar as the F is equal to delta P by delta T. Here the torque is equal to angular momentum for the time rate of change in angular momentum. Therefore, L2 minus L1 upon delta T. Substitute the value of angular momentum from Bohr's hypothesis, nh upon 2 pi. So, final angular momentum into h upon 2 pi, initial in 1h upon 2 pi upon delta. We end this equation. n2 minus n1 h upon 2 pi common, so h upon 2 pi delta t. Substitute the value n2 3, n1 2, h Planck's constant 6.625 to 10 is 2 minus 34 upon 2 pi 3.14. Delta t time interval is given 1.2 into 10 is 2 minus 8. And this simplified, we obtain the answer is 8.79 into 10 is 2 minus 12 Newton into meter. So, no any question are difficult, but require some knowledge about the equation and also the relation between the equation. What are the quantity we have to find out, whatever the data is given in the question. So, combine this quantity. Generally, the question depends on the energy, angular momentum, radius, and also corresponding to the wavelength. Clear?